Recording. Recording makes it real. So welcome back, folks. Happy Garbage Day. Couple announcements with respect to schedule and materials. So I did finally finish the end of example 4, which was the CFA example where I showed that you can estimate the same baseline models in SEM and a one-factor model using multi-level modeling software. So this is just a separate little video that I made for folks who are trying to learn both of these things to help with the correspondence between the two, because latent variables and random effects are indeed the same thing. So that is posted at the September 29th date, because that was where we finished that particular example. So I just stuck the video up here. And I just updated grades this morning with respect to homework 2. Not everyone has finished it, which means that I can't go over it as a group, but if you have questions about why you missed something or what the answer should have been, please let me know. The next thing that you have then to work on is not coming to class on Thursday. Can you handle that? Because I'm leaving town tomorrow morning, so there's no office hours tomorrow, no class on Thursday. And in my place, I left some things for you to do. So first up, your next formative assessment, number 3 for this class, is available and is due on Monday. And also, if you are one of the folks that did not get full credit on your homework 1 because there was information missing, that is also due on Monday. There is a separate spot in Icon to submit that assignment. And I would like for it to get done by then. That way I can make sure that I weigh in on your plan to complete homework 3, which is the next thing that's due the following Monday. So hopefully you've got a chance to get familiar with M+ code or Lavon code in order to estimate CFA models on your own data. One thing I wanted to mention is that several of you have multi-factor scales that you're interested in. And so in my notes back to you in homework 1, I said just pick one. If you want to do more work, that's okay. I'm okay with reading more if you want to do more, but I want to try and keep the scope of the assignment comparable across students. So you only have to do one factor if you have at least 6 items. If you don't have 6 items, then 2 factors so that you get enough items to have things go wrong is sort of the idea. If you have any questions about what you should be doing with respect to what data are appropriate or going to work, please let me know. And I had meet on Zoom only for next week ? Because I wasn't sure if this setup was going to work, but lo and behold, our lovely tech people have gotten it to work for us, even though the main system is down, so thank you very much to them. So I am going to meet in person next week. I will take this off on Tuesday. Thursday of next week, though, on the 20th, we are going to be on Zoom because I'm getting kicked out of this classroom for comprehensive exams again. So that's not on me or the technology. That's just the scheduling. So we will be on Zoom next Thursday. All right. Any questions about logistics, homework, due dates? Yes, sir?
What's the content for Formative Assessment 3?
Formative Assessment 3 is a little bit of CFA and what's a logit and what's a probit.
Okay.
So the idea is, since you're going to start doing the CFA stuff on your own data, I wanted to review more about the indices of fit and what they're telling you, and then start reviewing this unit stuff. Because homework 4, which is not for a while, but in about a month or so, will be practice with IRT and IFA, and then you'll get to try that on your own data as well for homework 5. So, any other questions? Good to go? All right, then I will shut this down. What I have is lecture 5, and I have example 5. I'm not sure how far we'll get, but we'll see. So last time we were continuing to start with the idea of factor models for binary data, and there are 2 different sets of models and corresponding words that are algebraically equivalent that we're talking about in this unit. So one is IRT. What does IRT stand for? Item response theory. Yes. No. Not to be confused with, regression theory or structural equation modeling theory, but it's a theory. It's IRT. How about IFA? What does that stand for? Item factor analysis. And that one is otherwise known as CFA for categorical indicators. So that's the bigger picture of where we are, these models, where we have, where we were last time in particular was IRT models for binary data, So then I have up here the one that I think is going to be most useful to us if you have binary items, the two-parameter logistic model. So in these models, which of the parameters are item things and which are people things? Start with that. I'm on slide 31.
Items are eye subscripts.
Yes, the ones that have eyes. Yes, not a coincidence. Throwing softballs at 2 in the afternoon here. That's what we're doing. So we have an A that has an eye and a B and has an eye. Those are both fixed effects, meaning that each item gets its own. Then that leaves this person here to be a people thing, S for subject. What's that name? What is this thing? Zoom it in. Oh, not that far. What's that thing right there?
Theta.
Theta. What is theta?
Something.
Latent something. Factor score, latent trait, latent variable, true score. Am I losing any? Ability, yeah. Or if you're not in an educational context, like some other kind of person characteristic, a person tendency, something you can't observe but you think you can by asking questions about it, try to put it together. So theta is our latent trait in this unit. Everyone has decided to call it theta. That's not just me, so that's why I'm switching the terminology. And what's the difference between writing the model this way and writing the model that way? Because it has the same ingredients either way.
Link function.
Link functions, yeah. What's on the left-hand side is the difference. So logit, what's a logit? Cough, cough, quiz question.
Log odds.
Log odds,
Over probability of a 1.
yes, the log of the odds of a probability of a 1. That's what a logit is. And why do we need it? What's it for?
To deal with balance. Bounding your responses.
Yeah, so to keep the predicted probability between 0 and 1 like it's supposed to be. So if we take the model predicted probability, so the conditional mean of the model, and transform it into a logit metric, that takes it from a 0-1 bounded variable into an unbounded continuous variable. And where is the neutral point where probability would be 50-50?
0.
0. So a logit of 0 corresponds to a probability of 50-50. If I said that the probability of a response of 1 corresponded to a logit of 2, then what is the probability of a response of 0 instead?
-2.
-2, yes. Yes, logits are symmetric about 0. So if I write it this way, then this is the probability version of the model, where it's e to the model prediction over 1 plus e to the model prediction. So you can always get back and forth between these. So A then, in this model, is a slope. It is directly analogous to a factor loading in a CFA model. It controls how well the item is thought to measure the trait. And if I take this little I off of here, and I make all the items share a common A, could I do that?
Yeah.
Does it have a special name? If I take the I off and make all the items share a common A? 1PL. So I say 1P because L goes with logistic, and we could be using probit. But one parameter model would work. Yeah, 1PL is logit specifically. What would you call it?
Tau equivalent.
Tau equivalent model, yes. So we had this idea in CFA, not a coincidence, by the way. I was setting up for this. The idea that you can constrain the loadings to be equal and see if it hurts the model fit. If it doesn't hurt the model fit, you could view your items as equally discriminating, and that's fine. There's another special name that goes with this if you take the I off and make all of the items share the same A discrimination. Starts with an R. Roche. Yes, that's a Roche model. So Roche models are a family of models. Their common thread is that none of them have an A sub I. It's all A. So all Roche models assume that the items are equally discriminating. Doing so has certain benefits, but to me it has the cost of not being right, particularly if you're dealing with items that assess attitudes or people have to agree with statements or behaviors where they're certainly going to be difficult to make exchangeably good. So factor loading then is analogous to our A in this story. B is its own animal. So B is known as item difficulty. In a non-educational context, it would be called item severity. And in this metric, more means more. So a higher B value means it's more difficult or more severe. It is a location parameter, and its definition is the amount of trait needed to have a 50-50 probability of endorsing a 1, a correct response, or saying, yes, I have that symptom, or whatever a 1 means in that context. So it is related to, but not the same as an intercept. They're not quite the same, but they cover the same kind of idea. So more coming on that in just a little bit. Okay. Any questions or things you want to ask about otherwise thus far? Yes?
Which one's the more threshold interpretation?
Thresholds are not in this story.
Okay.
Thresholds are the IFA version of the same model. Is that an acceptable answer for now, or do I
Yep,
need?
no.
Okay, okay, it's
No.
coming. It's coming.
Great.
So there is IRT models have A's and B's. IFA models have loadings and either an intercept or a threshold. There is a direct mathematical correspondence between the two. So it's not like one is better than the other. They're just different ways of describing the same thing. This is not a threshold. It is a difficulty. And the reason that I'm starting with this is because I like it. That number that it comes out to be is directly informative as to how difficult this item is. How much theta does it take to get this right? 2? Okay, that's a hard item. -1? Not that hard. Thresholds give the thresholds give the predicted probability of a 0 response, not a 1 but a 0, when theta is 0.
Right.
So a threshold describes what would happen if you were average, which is to me less useful than, well, what if not everybody's average? So the B meets you where they are. Like it tells you how much trait is needed, which it's much more useful, I feel like. So, and this is IRT. So we got our 2 parameters here. Is that all we can have? We close up shop, we're done? Or could I have 3 or 4? Could. There's probably more than that. They may be up to 5 or 6 by now, because I don't keep up in this field as much as the other fields. But yes, we can add some more to it. So the predictions of a 2-parameter model, we looked at this slide last time, but just to remind you, the lines that are in blue share a common B, which means they have a similar point of -1 on the latent trait where their probability intersects at 50-50 here. So somebody of a theta of -1 has a 50-50 shot at getting these 2 blue items right. What differentiates them is their A parameter. The darker blue has a smaller A, is less discriminating than the lighter blue. So all things being equal, if you want to measure somebody well who's at this range of the trait, you pick light blue. Same thing with the 2 purples. These items are, we call these more difficult or less difficult.
More difficult.
These are more, so it is the right way. So it takes a trait value of 0 to have a 50-50 shot at getting these right. Somebody who has a trait value of -1 has a much lower probability of getting these right. And the pinky one has the stronger discrimination relative to the purpley one. And why Roche people would say that this is just bananas craziness is because they intersect. And if you follow the curves long enough, they get out of order with respect to their difficulty, and that is viewed as a problem. So that's a violation of what is known as specific objectivity. All right, so then we looked at the end, a few other options that I'm just going to say this exists, and that's all I'm going to say. Because in the context of a attitudinal measurement, psychological measurement, you don't see this as much. In the context of academic measurement, it's much more useful. So C as another addition to our model. So it starts with B, then we add A, and then we add C. You would think it would be the other way, but it is not. So C is a lower asymptote. The idea is that it is the probability of a correct response that is separate from theta. So no matter how low your theta is, the lowest this model predicts your response to be is a probability that goes with C here. So then 1 minus C controls the rest of the curve as a function of A and B and theta. So this is known as a guessing parameter. Some people would say, it's not really that. It's a lower asymptote. And I say, whatever. It's difficult to estimate unless you have a lot of people, and a lot of people at the lower ability level where C would be most relevant. So this is one that takes a lot of data to make it work. And it changes the interpretation of what B means because it doesn't correspond to 50-50 anymore, but B is still a location parameter in the same type of interpretation. And where we left off with is if I can have a lower asymptote, well, let's have an upper one too, and I'm going to call that D. D is used as an intercept in other versions of IRT models, and so D doesn't always mean the same thing. But this one is, if C is guessing, D is known as carelessness. So if the probability of a correct response doesn't get all the way to 1, even at the highest level of ability, if it asymptotes below that because of carelessness or deliberate not answering the question in the way you could because you're trying to lie or look good, that's what D would come in. So this one then would need a lot of people at the upper end to be able to figure that out. So this would be about the most complicated model that I would see for each item. All right, I think that was about where we ended up last time. So for parameter, the logistic part then is specific if you're using a logit. What's our alternative if we're not using logits? Probits, otherwise known as z-scores, otherwise known as, starts with an O. Ogive. That's what ogive is probit. What is a probit?
It's a differently scaled.
It's a link function. It solves the same problem that logit does because it takes the probability that's bounded by 0 and 1, and it stretches it out into something that goes on forever. And it's also symmetric, where a probit of 0 is 50-50. So what a probit is it's the z-score under the standard normal distribution that goes with the probability for the area to the left. So it requires integration to go from probits to probabilities instead of a handy-dandy equation. Now, I wouldn't even bother talking about probit if it weren't for the fact that in certain types of estimation, you're stuck with probit. There's no logit choice. Such as when you use Levon for these models. Anything that uses limited information estimation, meaning we start with a summary of the data and the model operates on the summary, you're stuck with probits. So that's why we have to know the difference. The difference between logit and probit, if you want to rescale one set of estimates into the other, they differ by a factor of about 1.7. 1.701 to be specific, but 1.7. Yeah, somebody figured out that 1.701 worked better. Like that was somebody's contribution to the world. So I don't want to minimize it, but 1.7-ish is enough. And that's one of those numbers that sometimes shows up in these formulas, and that's why. Is because they're trying to take a probit scale and blow it up so it becomes logits. All right. Questions before we continue further? So let's talk about reliability. That's what we're transitioning to, because we need some new words. But more important than new words is we have new concepts as to what reliability means in these models and how it necessarily differs from what it means in CFA models. So I'm going to make this big. So first off, we have the same problem in CFA that we are dealing with a latent trait that's imaginary. Every latent trait in your IRT model needs a scale. It was called model identification a month ago. Was it a month ago? I think it was about a month ago. Now it is anchoring. But guess what? The solutions are exactly the same. So we have to fix the mean side of the factor and the variance side of the factor. So we can either anchor by persons, as it is called, which means that we fix the distribution of theta to have a known mean and a known variance. Almost always mean 0, variance 1. In this approach, you can estimate all item parameters without constraints. So this is analogous to what I recommended in your CFA homework 3, as well as what I personally prefer. The benefit of doing it this way is that you immediately know what a theta means. Like if I told you I have a theta of 3, your response would be, wow, congratulations. Unless theta is measuring like psychopathy or something, then maybe 3 is not great. But you know that 3 is a lot. Whereas if I pick one of these other scalings, it's like, my theta is 3. Good? Like that seems high, but I don't know how high the scale goes. So this method makes it so theta has a very interpretable metric. And in this case, if you wanted to fit a Roche model, the common A would have to be estimated. So you would basically tell the program, hey, make all the A's the same, but figure out what that A should be, because it has to be estimated given theta's variance has been fixed to 1. The other way to do it is anchor by items, which corresponds to the marker idea in CFA, where you would fix one of the item difficulties to 0, or their mean across items to 0. That's another alternative that you may see. And on the variance side, you would fix one of the item loadings to 1 and estimate the theta variance instead. And in this case, if you fit the Roche model, all of the A's are 1, and the factor variance is estimated instead, which is why A disappears from those equations, because it's 1 at that point. But it can only be 1 if you're willing to estimate theta's variance. Otherwise, you're saying the items are not only equally discriminating, but perfectly discriminating, which is not cool. Question?
And so when we're talking about like equating, and we use anchor items to do that, is that a different concept than anchoring in this case?
It's slightly different, but it's related. So the question was, if we're doing some kind of equating where we're trying to put different sets of people or different sets of items onto a same scale.
Yeah.
By the way, Jonathan says calibrating is the same as estimating. I checked. Like, am I missing anything? Or are these just synonyms? He's like, yeah, they're synonyms. Calibrating sounds kind of cooler, though, right? It sounds like there's more involved. To me, estimate means find the answers. How do you know that they're the right answers? Well, we have to choose your criterion. Does it make the data the tallest? Does it make the error the smallest? Does it, like what are you trying to find? But estimate and calibrate are the same. So in that context, if you are doing a joint estimation, then an anchor item is something that is, its parameters are constrained across samples or sets of items so that you're holding the scale of theta and what it means constant. So it is kind of the same, but it's across samples or versions of a test or something like that. Another way of saying it is that it is an assumed invariance constraint. But the only way that you can make it work is if you're willing to make that assumption.
Yeah. I'm probably just going crazy because it's week 8, but like you need, in order to make yogurt, you need yogurt. You know that? So it's kind of...
Okay, the question involves yogurt, and I'm missing the thread here.
Because like in order to make yogurt, you have to use yogurts. In order to keep the scale the same, you have to use questions that have been already like...
Okay, I don't know about the yogurt part.
Yeah, it's probably just my brain.
But, because I don't cook or bake or do anything that doesn't involve a microwave or boiling water. But I can say that if you have like a set of anchor items, so like you have like, I have 2 samples of people and everybody gets items 1 through 10, and this group is going to get 11 through 20 and some other group is going to get 21 through 30, like that kind of thing.
Yeah.
Then not all 10 have to be exactly the same. You can actually test invariance with the 10 and hold the ones that are that do work out to be the same or close enough equal, and let the other ones not be anchor items anymore.
Okay.
If you have enough, you can test it. Mathematically, you need 1 to hold the scale together. You need 1. Now that is a terrible idea in practice, but the math works. Yeah, enough in common to where you can say, yes, this is the same trait and it's reasonable to tack all these extra items onto this common 10. But yes, anchor is another term that's used in different ways to mean different things. Kind of the same, but kind of not. So point being, everything that you've already learned about how to scale your model still applies. The end result of this, so for those of you who've never seen these models in M+, does it sound like this would be hard? Like to estimate IRT models, since they look so different and everything? Like when I first saw this, I was like, oh God, how am I gonna do this? When I first saw this, it was in grad school and I was using Bilog and all these older programs. The code that I gave you in M+, add one line to. That's it. The code that I gave you in Levon, add one more option to. That's it. So, and these numbers, if it's binary data, the A's and B's just fall out of M+. They don't fall out of Levon though. But it's not nearly as bad as you would think, because the model gets estimated in the IFA version, which you can backwards engineer into this version. Okay, so point of the story, every theta needs a mean and a variance. You can set the mean to 0 and the variance of 1 if you want to, or you can fix one of the items to have a marker loading that's set to 1 and a difficulty that is set to 0. Those are your choices within most common software. There's other choices as well. All right, so now the big one, information. Information is the term that is analogous to reliability or measurement precision in these models, and it means the same thing, like how precisely have you measured this trait? In CFA models, one can compute information. The formula for it is the unstandardized loading squared divided by the error variance for that item. Nobody bothers to do this, and for good reason. Because if you computed information across all of your items, and you also have their standardized loadings, you would come to the exact same conclusion as to which items are relatively best. The standardized loadings tell you everything you need to know. So nobody bothers to compute information for CFA. Now, do you see theta anywhere in this formula? No. So what does that mean we're assuming about information?
Constant.
Constant. Right? We computed an omega value, a number that was reliability for my factor. What about low people? Omega. What about high people? Omega. What about medium people? Omega. And the reason for that is because in CFA, information is indeed flat. So in that world, an item with a better loading is a better item for everyone because the loading is linear. It makes it that a 1 unit increase in the trait has the same change in the predicted response all the way across theta. So if we were to make a test information function in CFA, it would be flat. So here's some numbers to go with these ideas. These are two items out of a set of 6 items that we played with before, where the scale is 1 to 7. And item 6 here has an intercept of 5.3. So at 0 here, my little line is crossed. At 0, that's where the red item intersects. That's right there. It has a loading of 0.82 and an error variance of 1.67. So the information for item 6 would be computed as this. Item 1, meanwhile, has a lower intercept at the 0 point, but it has a steeper slope, so it has a stronger loading, and its information would be higher. So Y contributes almost twice as much information as, or Y1 contributes almost twice as much as Y6. If I were to look at the 2 standardized loadings, I would come to the same conclusion that item 1 is better. Better for whom? Everybody. That's the assumption that we're making. Now, that is not the case in IRT land for binary items. What happens to these lines when you're predicting IRT from an IRT model instead? Yeah, I'll take the gestures, right? This is a gesture question. It's like an S. Or that way for you guys. There's my S. These are my boundaries. That's what we got here. Yeah, it's bendy, right? So the bendy line means that it has to shut off at some point. So it's not going to be equally good for everybody. So the information that the item contributes depends on where it is on this location. So fortunately, we can take information that's in this relatively strange metric and we can convert it to reliability with this simple formula. Information over information plus 1 puts it into a 0-1 reliability metric that everybody will know what to do with, even if they don't know what an IRT model is. So I have in the example 5 packet, I have a giant spreadsheet that has a bunch of different tabs. One of them is information and a conversion of information into reliability that you can borrow. So in IRT, we will start with this information quantity, convert it to reliability. But the whole point is that it's no longer going to be one number. Each theta potentially has a different reliability that goes with it. It depends on how many items are in that realm, in that range, and how good they are. It is technically possible to come up with a composite reliability by taking your function, weighting by how many people are at each theta, and then coming up with a number, but I don't feel like that's useful. So I'm not going to do that. So then if we translate what the CFA model would predict versus what an IRT model predicts. So we'll start with the CFA functions here. We have the blue item has a stronger slope for everybody than the red item. If we were to compute information based on its model parameters, the blue item's information would be just under 1. The red items would be just under, or about 0.4 or so. Then the IRT model. From 2 of the lines from here, the light blue one and the pinky one here. I added this box, by the way, so this is a new box relative to the version of the slides that you have, because I realized it didn't actually tell you what the formula was, which in this case is very easy. Information is the discrimination squared times the probability of a 1 at that point and a probability of a 0. So these nonlinear slopes relating the trait to the probability of a 1 translate into these kinds of information functions. So these are called item information because it's per item. So these two right here are at the same point on theta. The pink and purple both have a difficulty of 0. So their function is centered at the highest point of 0. Apparently, so there's a winner of Shark Tank outside here. Congratulations to whoever just won. Hope you can finish the pizza. But of these two curves, the lighter pink one is steeper, right? So that translates into more information at that same point. So both of these items are designed for people of middle abilities, but the pinker one does it better. Test information, then, is literally the sum of these curves across all of your items. And that tells you to what extent you have precision along all of the range of theta. So for instance, here's some more curves. Here are 8 items. They vary in difficulty and discrimination. So 2 of them are at difficulty of -1, 2 are at 0, 2 are at 1, 2 are at 2, and they each either have a discrimination of 0.5 or 1. So that creates these curves right here. So I have the item numbers here. If I want to measure people who are very high in my trait, which items are going to help me do that best? Yeah, 7 and 8, these ones. If I want to measure people who are low on my trait, yeah, 1 and 2. I tried to make the math easy so we could play along with this. So these same curves then would translate into information curves that look like this, where the items that have the same difficulty, their curves are centered at the same place. The ones that have more discrimination, though, are higher at that place. So all things being equal, if I wanted to make a short form, which do I pick? The taller ones. Yeah. So it's not just how discriminating they are, but where are they that discriminating? If I didn't have this pink one here, I would probably still want to take this lower blue one at the same place. It's not as discriminating, but it's designed for people who are low, whereas the other ones are not. So this is the part that gets trickier in trying to figure out what items you could potentially keep versus remove. It's not just about their content. It's not just about their discrimination. It's also about their location. Location didn't matter in CFA because the lines kept going. Location matters in IRT because the lines shut off. How are we doing?
I think I missed how we go from the curvy lines, the S lines, to
Yes.
these.
To these?
Yeah, can you?
This box. So this, I just added this like a
Great.
couple days ago.
Thank you.
Yes, that's why you literally missed it on your copy, because I just added it.
Okay.
So I realized that would be helpful. But yes, the formula for information is basically how discriminating and then where it is in terms of probability. So it's analogous to the formula for information in CFA, which is loading over error variance as well. So loading is the driver of how much, but where is the question. Error variance in CFA is constant across the trait, whereas here in IRT land, it's not constant. So the key idea here is that not all items are created equal. Location matters. Just think of it like real estate. Location matters. I know. It's a weak one. I'm trying.
Right, but we could have two houses that theoretically are the same,
Mm-hmm.
and one's in front of a park,
Yeah, location matters.
and one you're in a neighborhood with a bunch of undergrads.
Yeah, that would be less desirable to in a neighborhood with a bunch of undergrads. But items that have low loadings or low discriminations could still be good items if they capture a range of the trait that the other items don't. So it's a redefinition of what good is. It depends on what you're trying to measure. Like, who are you trying to measure? So this is a picture of test information, and how it is often presented is how it translates into the standard error of theta. And they are telling you the same thing, just in an opposite direction. So the more test information you have, the lower your standard error is. And this type of curve would be expected to result from a test where most of the items are mid-range in difficulty, and we have relatively fewer items that are out here on the positive side or out here on the negative side. And that would cause their standard errors to go up. So this is the big difference, is that if someone tries to say, like, oh, what's your alpha for your binary set of items? You're like, no. Because where are they? That's the question. So the way that you would have to talk about this is to literally give the function for information, or to say, I have information that is adequate from this range of theta to that range of theta, where adequate is some kind of threshold you'd have to define. Cut point. No one say threshold. That's a different thing. Cutoff. So how do I know if this curve is good? Because I never learned this when I learned IRT. I learned this much later. Is 4 good? Is 3 good? Exactly. I didn't know this either. And as proof that I didn't know this picture was in my job talk. So I gave 3 different presentations. I interviewed at Syracuse University, the University of Nebraska, where I eventually took the job, and Penn State University, proudly showing this picture, okay? This was from my dissertation, where I made up a new measure of visual attention, basically selection or orienting in space, and people's ability to do it efficiently, quickly, etc. And I was super proud of my information function that resulted from this test, because the goal of the measurement process would be to eventually find people who have deficits, like older adults who are showing attentional deficits that might lead them to be unsafe drivers, or maybe not be able to live independently, or those kinds of things. So we're looking for people who have problems. So the point that I was trying to make in this picture is, look, my information function peaks in the low range, which is exactly what I want. If you're good at my test, it doesn't really matter how good you are, because I'm not concerned about you going home and driving or living independently. So I was all happy about this. Unfortunately, nobody asked the question, is 2 good? And I have uh-oh here as a foreshadowing. What does this become in reliability? Information over information plus 1 is reliability. Oh, uh-huh.
So 67 67%?
Yep, 67% reliability. And I'm all, look at this. Yeah, no, this is not good, as it turns out. The shape is good, but I don't actually have a lot of information. So in conveying these results, what I have coached people to do and what I think is more useful is to put it in a reliability metric so that people know what the y-axis means. Because no one knows what information means. Here is another example of what information would mean. 8 is a good reliability, or yeah, an 8 information would be great. 8 out of 9 then in that case. If you wanted to measure people because you're trying to make a decision, like you're trying to measure students who would qualify for gifted education or something, this is the kind of information function that you would want then. You want to maximize information around the point where you need the most precision. If they're really not going to get into the program, you don't need to know how good they are or how bad they are. If they're really, really talented, they've made the cut. It's the middle point. However, if what you're trying to do is classify people, there is a different model that might work better. And it is known as either cognitive diagnosis models if you don't go to school here, or diagnostic classification models if you do. And I have a link to a textbook that you might recognize some of the authors, Diagnostic Measurement. And I had to put this in here because I Googled the book so that I could get the link to it, and this is what the Google told me the authors are. Jonathan Templin, mathematician. Robert Henson, author, and Andre Rupp, author. So he got elevated by the Google, not just psychometrician, mathematician. The other guys, yeah, screw you, you're authors. So I'm not sure they would be pleased about that distinction, but I found it amusing and I wanted to share. So in these models, diagnostic classification models, theta is a binary variable. So if I say that CFA and IRT are as to regression, diagnostic models are like ANOVAs, but in latent space. So you would tell the model, I think there's 2 groups of people. I think there's people who've mastered this, and I think there's people who haven't. Or people who are above the cut, or people who are below. And if you're somebody who's above the cut, you're going to have a higher probability on this item and this item, but not on this item because it doesn't measure that theta. So you put in this pattern of how you expect people to do through a whole series of constraints, and then you can test whether or not your view of the world is consistent with the data. So if I think I have 2 traits, and some items measure one and not the other, then I would say for items that don't measure that trait, there's no difference between these people. For items that do, one should be higher than the other. And you can also have items that measure multiple things. So for instance, if you have a math item that requires order of operations and addition, then that item could measure both traits at the same time, whether you know how to do order of operations, whether you know how to do addition. So if your goal is classification, getting an IRT theta only to cut it up is kind of a waste of time. Because you don't need to know how low the low people are or how high the high people are. You need to know like right in that spot. And there are models for that. So there's my shout out to the rest of the classification literature with respect to test information. So there's not good or bad when it comes to test information. It's what shape do you want? Like who are you trying to measure and for what purpose? So then how do we improve our reliability? Get more items is the answer in classical test theory. Get more items that load more highly is the answer in CFA, because according to CFA, a linear relationship between the trait and the item response means that information and reliability is constant. But in IRT, it's get more items in the range at which you want to measure people with a corresponding amount of difficulty. So content aside, higher A items are going to be more useful, but in order to measure the whole range of the trait, you would want to make sure that you've got items across the board. How are we doing? So this is, I think, a different way of thinking about it for probably not educational folks, but for the rest of us. Like those of us from sociology, psychology, the rest of education who's not doing testing per se. If you're trying to measure attitudes or tendencies or things, it's like, who are you trying to measure? Are you trying to measure folks who might need help? Are you trying to measure folks who are really good, or do you want to get everybody? if the answer to is I want to get everybody, and I want everybody to be measured well, then a fixed format test is probably not going to do it. So this is a picture that I borrowed from the Embertson and Reese textbook. Note that there's a typo in it that I fixed here, where she's trying to show the difference between what an adaptive test can do and what a fixed format test can do with respect to standard error. So the whole idea of adaptive tests is that you don't waste people's time with items that are too low or too high. And if you can customize the set of items to be right in the range where the people are, then you can maintain the same degree of precision across the board. Whereas a typical test would have standard error distributions that look like this. It's the opposite of information, which would go the other way, where we would have larger standard errors on the ends because in most cases you would have fewer items out there. But it's up to you. All right. Another thing, adaptive testing to solve measurement conundrums. So one way that this type of idea of not wasting people's time can be leveraged is with longitudinal data. So if you're measuring children and you want to measure children's growth over time, that can be quite tricky because you need to change what you're asking them to do so that you can maintain age-appropriate sensitivity. But you also want to be able to measure the same trait. So a compromise is to do a linking design, or anchoring is a synonym for that, where you have a common set of items that are given at all occasions and you swap out the other ones deliberately so that you can maintain sensitivity at different points on the ability continuum. So the term for this is vertical scaling, otherwise known. So like if I have people of younger ages that should be of lower abilities, I can give them easy items along with the common set, and as they grow, we can drop easy items and move on, and we can still maintain the same kind of trait. So this can be done in CFA as well. It doesn't get talked about in that format, but the same ideas and rules would apply. So the same thing would happen if you're measuring different samples. So let's say that you're measuring children who come from intact families, children who come from families of single parents, and children who come from foster homes. You might ask them some of the same questions about their experiences and their lives and their feelings, but certain questions may not be relevant. Like, how often do you eat dinner together as a family? What does that mean if I'm in a foster home? Like, do I consider like all the children that are in the home with me my family? Like, do we all sit down together? Like, maybe that doesn't mean the same thing or it doesn't is relevant. You don't have to give those items to the kids for whom it's not relevant. You don't have to give all the items to all the people if they're not going to be useful. And as long as we're in latent trait land, that's a huge advantage. That can solve problems of sensitivity. That can solve problems that are accidental. So like, what if I forgot item 9, right? That kind of thing. If you're just doing sum scores, a sum total without item 9 doesn't mean the same thing as with item 9. But if you can do a joint equating calibration kind of thing, then you can potentially get away with not having item 9 for some people. So just want to point that out there. There's a whole world about this, and I think it's really cool. But the idea that you can change your items and still have the same trait if you do it carefully is a huge advantage in real-world measurement. Right. So I went to a presentation, I think it was at KU, about these models, and where this was one of the first examples that I saw of how you can leverage this to be able to work with existing instruments that are not quite right. So this was an example of measuring physical function, where there are two commonly used measures that were the focus of this example. One is known as the SF36, which is given to just regular folks, where the items are things like, can you run a marathon? Can you do this? Can you do that? Where the bottom of the scale would be like needing help being able to bathe yourself. Like that's the lowest item they have. And there's also a scale called Activities of Daily Living, which is often used for older adults as a screener for who might need help. And so then their scale goes even further. Can't maintain balance, can't stand on their own, that kind of thing. So if you were trying to measure activities or capabilities of folks, but they weren't quite this low and they weren't quite that high, you could take items from both and put them together. So you can customize your measurement using existing items and existing scales if you can put them all together. So they built this combined metric in this example of basically taking the best of both and putting it onto one ruler. And I thought that was super cool, especially if you're working with, say, archival data where folks may have given different scales for the same construct. If there's any kind of overlap, you can link it back together again by constraining the parameters to be the same and linking them onto the same trait. All right. I have this article in here. I have a couple slides about that, but I don't want to belabor the point. I think they did a really nice job of describing this process. It's an older article, but it was readable, and I like their pictures, which is why I picked it. But one of the things that they talk about is this idea that theta is supposed to have interval measurement if you have enough items. That is true, whereas some scholars don't. So they were trying to put together measures. A mini mental status exam is what this stands for. This is used as a screener for dementia in older adults. And so they had this total score that links what the relationship between what theta would be and what the total score is. And they're pointing out the difficulty in trying to talk about change in this trait. If you're doing it in a total score versus a latent score, the same amount of change is not comparable at different points. So it becomes tricky to talk about who's losing capability over time. You might come to a different answer in latent space than you would in some scores. So they also then tried to take 3 different measures and stick them together to get a better estimate. And their curve then, after they did that, worked a lot better. The top still flattened out because they didn't have enough high items. And so to be able to even further measure people, they would want to add some stuff out here. All right, 255. Can I answer your question now, Nikki?
Sure.
Okay. So I told you this was factor analysis, right? Here's the part where I prove it. And this is going to be a lot, and we're going to go over it next week, but I want to just plant the seed. And I said the word prove, right? You heard me. Because this is one of the few instances in which I can say prove. Because we're talking like math, prove. And I didn't prove it. This has been known since the 70s, probably even before then. So here is how all of these different models relate to each other. Because IRT looks like it's completely different in the way it's written, but it's actually not. So if we start with linear regression, we have the outcome for each item in each subject is a function of that item's intercept plus that item's slope and some residual. That looks a lot like our CFA model, just with a different set of notation. But the interpretation is the same. The intercept is the expected item response. The slope is how the item response changes per unit of F, and E is the difference between what's predicted and what you have. Cool. If I say, no, I need to make this for binary items, okay, I can do that. So the right-hand side stays the same, but we switch the left-hand side to predict the logit instead. That way, when we back-translate logits into probabilities, they stay between 0 and 1. And E drops off here because variance is no longer a separately estimated parameter, and it's no longer constant. It's tied to the predicted probability. So we have this version of logistic regression, and then we have this version of an IRT model. And they look like they would be completely different from each other in the way they're written. The left-hand side is the same, though, which is setting us up for the idea that indeed they are the same. So we have binary regression models in which we can write the linear model in the usual way so long as we're predicting the logit or the probit. We have item factor analysis, which looks kind of the same. We have something that looks like an intercept sitting out front. We have a factor loading, and we have our friend F here. This new term right here is a threshold. It is an intercept multiplied by -1. So this version of the model, item factor analysis for binary data, looks a lot like our CFA model. The only difference is we swap out an intercept for this threshold thing. But otherwise, we got a loading that does the same thing. We got a factor that does the same thing. And the right-hand side is the same. The left-hand side depends on what your link function is, whether you're predicting the logit or the probit. But they both serve the same purpose of unbounding the probability. So this is, when people do item factor analysis, these are the parameters that would show up on their output. You get loadings. If you're using M+, you get thresholds. If you're using other programs, you might get intercepts instead. But the key to why you can just stick a negative sign on this and have it work is because of the symmetry of logits and probits. So if I have a probability of a 1 that corresponds to a logit of 2, what's my probability of a 0?
Negative.
-2. So we can switch these two back and forth because of that property. So you either need an intercept or a threshold, and you multiply by -1 and you get the other one. A loading is a loading in either case. So here's the translation then of this red version into what we have, where we have A's and B's. It goes like that. So if I rearrange the model to look like an IFA model, then A times B is my threshold. A is my loading. And here are the conversion formulas that work if you have a differently scaled theta than a mean of 0 and a variance of 1. So A in IRT land is our discrimination, is the exact same thing as a factor loading in a model where the factor loading, or the factor is predicting binary responses, and it's multiplied by the square root of theta variance, which most of the time is going to be what? 1. So A is loading. Done. Tells you the same thing. Loading is A. So you can go back and forth. Now these ones, there's a little bit more here, but a difficulty can be found out of an IFA solution as the threshold minus the loading times the theta mean. What's theta mean usually? 0. That drops. So threshold stays, -0. And then what do we say theta variance is on the bottom here? 1. So that drops. So difficulty is threshold divided by loading. Or threshold is A times B. So you can get from one to the other. If you tell me what an intercept and a loading is, I can get you A's and B's. If you tell me what A and B is, I can get you intercepts and loadings. Why do we have the negative here? So that the thresholds and the B's go the same way. So that higher values correspond to more difficult or more severe items. So when you estimate this model in Levon, or M+, you get this. You get a threshold, you get a loading. You can take that information and turn them into A's and B's. If you estimate it in M+, it gives you both, actually, both solutions simultaneously. Question?
Does MERT give it in the IFA form?
MERT is, I believe, intercept slope.
Yeah.
Does that sound right? So then if you want to turn an intercept into a threshold, what do you do?
Negative B over A?
Nope.
Or,
These two.
oh,
Yep, -1.
oh, you negate it.
Yeah. So let me give you a picture to close with here. This is one of my favorite pictures ever. Slide 63. Maps all of these things on here. This is item 1 for example 5 that I'm going to show you. This is the item characteristic curve that describes how this item's predicted probability relates to the trait that it is thought to measure, where the trait is scaled with a mean of 0 and a variance of 1. Okay. So I can write out the model 3 different equivalent ways. I can say the logit of my item response is an intercept plus a factor loading times the factor, or -1 times a threshold plus the factor loading times the factor, or A times theta minus B. They will all give you the exact same answer. So this is what I mean by alternative parameterizations. Different ways of setting up the model and having it tell you things. IFA is the top 2. IRT is the third one. A and B is IRT. Hey, that math. Loadings and thresholds are IFA. And theta is F. So then on the picture, the loading and A are the same thing if your theta variance is 1. So in this analysis, A was estimated to be 4.3. So the logit of a correct item response goes up by 4.3 for every standard deviation difference in theta. So this would be a very highly discriminating item. And I can think of that as the discrimination parameter, the slope at the item's difficulty location, or I can think of it as a loading, either way. Okay, so that's the same. A and loading are the same. Now the other two. They each tell you about location tied to something being 0, but what is 0 differs. So probability of 1 in this metric, 50-50 corresponds to a logit or probit of what? 0, okay? So when y is 0 is when we're at 50-50, right? So that then corresponds to the B parameter in an IRT model. B tells you the amount of x needed to get to y equals 0. X is theta. So B tells you how much theta x is needed to get to y equals 0. An intercept tells you what y is when x is 0 instead. I'll say that again. An intercept tells you what y is when x is 0. A difficulty tells you what x is when y is 0. They're opposite. They're each tied to a different 0, x or y. So if we do B, then higher values mean the item is more difficult. This item has a B value of minus 0.3. So minus 0.3 is the amount of theta needed to get to a 50-50 probability or a logit probit of 0. I like that one. It's easy to interpret. It tells me who that item is for, basically. The intercept is the logit of probability of y1 when theta is 0. So the intercept tells you what y is when x is 0 instead. So if I go through the math, the intercept of this item was estimated at 1.6. That corresponds to a probability of a 1 of 0.8. So that's where it is on the y-axis. So for somebody with an average amount of theta, their predicted probability is 0.836, which converts into a logit of 1.6. So that to me is less useful because it tells me what that item would do for an average person, but not everybody's average. So an intercept tells you the probability of a 1. If you multiply that by minus 1, you get the probability of a 0 instead. And that's our friend threshold. There's your answer. I hate thresholds. Do you know why I hate them? Because look at the rest of the model that they're in. The rest of the model is still predicting a y of 1. But the first term in it tells you about a y of 0 instead. The loading then talks about y of 1. So it's internally inconsistent and it bothers me. But the reason people do it that way is for correspondence of its direction with the B term, where higher values mean it's a higher threshold means you have more of a chance of a 0, meaning it's harder. So threshold is your probability of getting it wrong. Intercept is your probability of getting it right if you're average.
This is the second class that you've talked about thresholds for me, so I think I just need to take a third one and I'll probably
Yeah,
get it by then.
Same. Yeah, It's not a coincidence, I swear, that in M+, they use a $ for thresholds, because it's like, if you finally learn this, someone will pay you the money, so they don't have to. This is confusing as hell. So thresholds talk about probability of a 0 for an average person. Intercepts talk about probability of 1 for an average person. B says, hey, what kind of person does it take to have 50-50? I'm just going to keep saying it like 8 different ways until it eventually sinks in. So
coalesced in my brain
Okay.
that I'm going to ask you to say it again.
I'm going to say it
so I
again.
can write
Okay.
it in my notes.
All right, I'm going to say it again. I'm going to say it correctly, too. That's my goal. So intercepts tell you about probability of a 1 for the average person. Thresholds tell you about probability of a 0 for an average person. Difficulties tell you what kind of person does it take to have 50-50. So intercepts and B's are just different points on this x-axis, essentially. They're both locations, but intercepts are backwards because higher means it's easier. Thresholds go the right way, but then it's like, what the hell is that? Now, why do I want you to learn this? Let me ask you that question. I'm going to tell you, I'm not going to make you learn anything else today. But do you remember what I said about software for these models?
They're all different.
They're all different. And you are going to get a number out, and you'll be like, what the hell's that number? It could be one of 4 things. And so knowing all the different ways that people put this together can help you try to figure out what your number is. Is this an intercept, or is this a threshold? Is this an A, or is this a loading? The other reason is that because what else you want to do with your traits then dictates what software choices you have. So let's say that you want A's and B's and you want them out of R. Do you know how to do that? MERT, right? Probably other packages. Can you then have your latent trait predict some other stuff in the same model in MERT? No. It only does the IRT part, the measurement model part. You're like, okay, fine, I'll use Lavon. Okay, you can do these models in Lavon. Lavons are going to give you thresholds and loadings instead of A's and B's. But then you can have your theta predict other things. But I just learned Lavon requires complete data. It does list-wise deletion for these models. I know. That's why we're not doing Lavon for this stuff. So what else you want to do with your thetas then dictates like what options you would want, and then you're constrained into usually A's and B's versus loadings or thresholds because of that. So having the facility to go back and forth, because honestly the formulas are not that bad. I'll go back to them. Here they are. So this is for the theta parameterization in particular, which goes with probit. So not so bad. And yes, I have an example for all of this in code, because yes, not expecting you to figure this out on your own. But to answer reviewer 3 who told me that IRT and factor analysis have nothing to do with each other, hello!
That is one thing that I have a question about in terms of like, you have provided many a story of reviewers just basically like being like, no, that's entirely wrong.
They're all true.
I don't discount that, and I'm like, how frequently, like, is it every article that you submit that you get pushback on? Okay.
Well, yes. So most of my commentary is limited to things where I was like the methods person and I ran the models and I'm in charge of that section of the review. But yeah, I would say most articles have somebody who thinks they know methods and provides questions and or criticisms. But the last one, literally, this reviewer said that factor analysis and IRT are nested within each other. Like, no, not in any sense of the word nested. And then they said you should be doing a Roche model instead. And I was like, no, because the items are not equally discriminating, and I can demonstrate that. Like, no. So, yeah. And I did not make this up, right? Like, this is like 80, 81, maybe? Probably even earlier than that people figured this out. Because it turns out that estimation is easier for some of these cases than others, and that's why they go back and forth. So, yes. So, I have a slide on that. Here you go. So if you're publishing in a journal that's used to seeing structural equation modeling, tell them that you did confirmatory factor analysis with categorical items and give them loadings and thresholds. If you're publishing in a journal that's used to IRT, tell them that you did that and give them A's and B's. And tell them which software you use so that they can answer any questions they have about what that must have meant in terms of how your model was specified. So, yeah, these are true stories, unfortunately. All right, 3:14. Any last questions before we call it not just a day, but a week? Zoomers, anything from you? No? Got a cat? Rumors? All right, then I will not see you Thursday. Enjoy your time off and work on Formative Assessment 3. Let me know if you need anything. See you next week here.